All right, thanks everyone. Thanks for the introduction to Valio. This is joint work with Vitaly Feldman, Hui Wen, and Kumar Palwar. And this is a talk about some working differential privacy. Can people hear me well? Yeah. So first of all, what are some of the, what's some motivating background for what I'm going to talk about today? Probably most of us have smartphones, and we depend on certain nice features on our smartphones like autocomplete when we text or automatic spell correct. And you wonder, how do these things work? Well, probably they use machine learning somehow. Here's a patent by Apple on how things like this work. And if I zoom in on the bottom right, the abstract of the patent, I'll just read the beginning. Systems and methods are disclosed for a server, that's them, learning new words generated by user client devices in a crowdsourced manner. Okay, so crowdsourced basically means us. So they're learning from our data, from our text messages. So if only every time you text your friend, you send a copy to them, they then get all these text messages and they can learn, no, this is probably how I should autocomplete the text. Okay, so the setup is there's a server, like whoever is manufacturing the phone, for example, and they're all the end devices, that's our devices. And the server might want to know things like the following. There are many things they might want to know, but for example, let's say there's a histogram F, which is indexed by all the words in the dictionary, and F sub X is how many devices just texted the word X. And you can imagine maybe it's not words, maybe it's bigrams or trigrams. They'll help you do like autocompletion or something like that. So this sounds simple. Each device simply sends a copy of all its texts to the server. Every time you text your friend, you BCC the phone manufacturer. Okay. That's not going to fly because of privacy. Do you really want the phone manufacturer to read all of your text messages? Probably not. And if you go back to that abstract, the word privacy appears a lot. So learn from the devices in a crowdsourced manner while maintaining local differential privacy, a differential privacy system, privacy budget, privacy budget, privacy budget. So of course they're aware of this, and in their system design, they want to design a system that actually can, preserve privacy. And so this talk is going to be about how do you do that. Everything's okay? And the basic idea is to send randomized messages. So add noise to your messages. What do I mean by that? Imagine your text message is an image. You're texting an image to your friend. I'm just doing this so it's more visual. And actually, this is not really how anything is going to work at the end of the day, but just to visualize. So imagine that I went to the baby shower for my first child. This is a real picture from that. I was playing some game, who can drink from the baby bottle the fastest. And this is the actual image I texted my friend. And I can imagine adding noise to it, adding more and more noise. Or here it is with lots of noise. And what does the server want to be able to do? Right? So there are now n devices. Here the n is 25. There are 25 devices. Some of them might be sending that picture. Like maybe that picture of me drinking from a bottle went viral. Okay. So there are a lot of people who are sending that image. Of these 25, some fraction are sending that image, and maybe some aren't. And what the server wants to learn is that, this is a popular image that is being sent. It doesn't need to learn, it shouldn't learn who is sending the image, because that would violate privacy. Okay? We haven't really said what privacy means yet, but we don't want it to learn who is sending the image, that would violate privacy. It just should learn that this is a popular image. And maybe there's some way it can combine what it sees on the left-hand side, like average them or do something fancier to extract, this is an approximate image that looks popular. Okay. So the moral of, I guess, what we want is we want each individual message, like the message on the left, to look like garbage. Okay. So if you look at any individual device's randomized message, it looks like garbage. And that will protect privacy for some definition of privacy to be seen. But in such a way that the server can still extract useful information about the aggregate behavior of all the devices. But before we can do that, we need to know what exactly does privacy mean. And here's an example where this is actually real. I mean, I coded something to noisify it, and then I ran something to construct it. So here, I took that image of me drinking from a bottle, and I heavily noisified it. Okay, so I think probably from that picture you have no idea what's going on. And then to that single randomized message, I applied something called wavelet denoising. It doesn't really matter what it is, some signal processing algorithm. And I got the thing on the right. Okay? And to me that's scary because, remember, the definition of privacy is you should have no idea what any individual device is doing, only understand behavior in aggregate. But here you've understood quite a lot from this individual randomized message. You can almost tell that it's me, maybe even. I mean, you can tell that it's someone drinking from something with a jacket collar. You should be able to tell that. Okay. So we have to be careful with what exactly it means to be private. Give a formal mathematical definition, and then prove theorems about or algorithms actually satisfying this privacy definition. Actually, this is why in privacy. I've only more recently gotten interested in privacy. It's not something I had worked on in my past. But I think to me it's a very exciting area, and it's an area where there's it needs theorists. Why? Because, okay, with algorithms I think needs theorists too, but with algorithms, maybe someone a practitioner says, well, this algorithm is running well on my data, even though I don't have a proof that that's good enough, right? But with privacy, there's no such thing as heuristic privacy. It either is private or it's not private. And what does it mean to be private? It means there's a theorem. So it's an area where you basically have to have theory, otherwise you have nothing. So what's the idea? The idea is what I said before. Device I will send a random message MI that is only weakly correlated with its data. Its data is XI. Let's say XI is a word in the dictionary. And one individual device's message should look like random garbage, but the server should be able to extract signal from many messages from different devices in aggregate. And the privacy definition is differential privacy, and this is differential privacy in the local model. And what is the definition? The definition says, for each device I, and any message M that could be sent, for all x not equal to x prime, x is the data, so x might be a picture of me drinking from a bottle, and x prime could be a picture of a cat, like totally different data. The probability that the device sends message M, given that it's holding a picture of me with the bottle, versus the probability that it sends that same message M, given that it has a picture of a cat instead, these two probabilities should be very close to each other. The ratio should be close to 1. It should be bounded by e to the epsilon. Okay? If epsilon is 0, it means the ratio is 1. It's bounded by 1, which means it is 1. But it's bound, this ratio should be bounded by 1, and its inverse should also be bounded by 1, which means that it's 1. Which means that the probability distribution of the message you send conditioned on your data is the same no matter what your data is. So intuitively, that means that your message doesn't reveal anything about your data. So that should be perfectly private. You haven't lost any privacy. So if epsilon equals 0, I'll say it's perfectly private. And because low epsilon is good, we'll call epsilon the privacy loss. Okay, so the bigger epsilon is, the more privacy you've lost. If epsilon is infinite, it means this ratio could be arbitrary, which means you might as well just send your data in the clear. So if epsilon is infinite, there's no privacy. If epsilon equals 0, it's perfect privacy. And then you could ask about what about epsilon in between. Okay. So there are two regimes to keep in mind. One is the small epsilon regime and, let's say, medium-large epsilon regime. Small epsilon regime, think epsilon is 0.01. And then e to the epsilon is 1.01 or something like that. So the ratios are very close to 1, but they're not quite 1. So that's like very good privacy. And then epsilon large, like think like 6 or 7 or something. Not super large, but like a constant that's much bigger than 1. It's what's usually deployed in practice. And large epsilon means worse privacy. So like, why is that acceptable? Why am I allowed to deploy large epsilon in real life? Well, first of all, before I answer that, just realize there's a fundamental trade-off between what I'll call utility, or what's usually called in this area utility, versus privacy. Privacy is in terms of this epsilon that I already defined for you on the last slide. Utility is, remember, at the end of the day, the server is gathering all these messages and wants to extract knowledge from them. And utility is like the quality of the knowledge it can extract. Okay? So these two things are obviously in tension. right? Because if I want perfect privacy, that's fine. I'll just send 0, or I'll just send a random message that has nothing to do with my data. But of course, then the server doesn't extract any knowledge. It hasn't learned anything about the data. So no utility. The other extreme is that I send my raw data, then there's no privacy, but the server gets the best utility it can possibly get because it has the data itself. So you could ask, what about when I slide epsilon between 0 and infinity? The utility should also somehow kind of continuously maybe change. And indeed it does. And if I'm the one who's trying to provide services, like I'm the phone manufacturer, I'm trying to provide the best autocomplete that I can, then I want to get the best utility I can. I would love to have the raw data, but I can't because I made a privacy promise to you, or maybe there's some law that prevents me from doing so. So, all things considered, I prefer to make the epsilon as large as possible. But it turns out that for a lot of problems, small epsilon, like epsilon being 0.01, provably requires too much utility loss to be usable for the downstream applications. But there's a silver lining here, which is that there are other models related to local DP, like secure aggregation and shuffling. I'm not going to get into exactly what those mean, but, maybe I'll say a little bit. Shuffling is easy to describe. Basically, between the devices and the server, there's like another server that sits in between that receives the messages, and the only job it has is to randomly commute them and then pass them on to the main server. And you can prove that these works have proven that shuffling automatically improves privacy. Meaning, if you have a local DP protocol which has epsilon being 5, and you have a lot of users, enough devices, and you just run that protocol but in the shuffle model instead, you don't change the protocol at all, then the new epsilon is actually 0.01. I'm glossing over the precise details, but that's roughly what it says. Okay. Which means it's okay to run local DP protocols with largish medium epsilon if you're running it in the shuffle model with a large number of devices, or the secure aggregation model. Okay. So from now on, we're going to focus on largish epsilon. Think epsilon is 5 or 6, something bigger than 1. Yeah. It's not going to infinity, but it's a large constant. So before I go further, our particular problem for today is the following, which I guess I already mentioned. It's each device I holds some data xi from a finite set of size k. This implies a frequency histogram, where f sub x is the number of devices whose data is equal to x. And the server wants to recover an approximate histogram f tilde that is close to f. And we're going to measure closeness as mean squared error. So basically L2 distance squared, the average squared distance between fx and f tilde of x. So I divide by the universe size. Of course, f tilde is a random variable because the messages sent by the devices are random messages. Okay? So really, we're going to focus on the expectation of the mean squared error and argue that we want protocols where the expected mean squared error is small. Okay? And expected mean squared error small is not the only thing we care about. It will be the primary thing we care about. But there are 5 things that we care about. And kind of, if you fix 4 of the things on the slide, you basically want the 5th thing to be as small as possible. So what are the 5 things? One is the privacy loss. You already know what that means. That's in the epsilon that I talked about. One is utility loss, which is the expected mean squared error that I just put on the last slide. The expected L2 squared between f and f tilde. And then there are some efficiency things I care about. Right? So this is a distributed protocol. There are a bunch of devices sending messages to a server. I want to minimize the communication. So each device is going to send a b-bit message. I want b to be as small as possible. Then there's the server time, which is, again, the server is going to collect all these messages, and messages, one from each device. And it's going to run some algorithm on them to extract f tilde. I want that algorithm to be as fast as possible. And lastly, device time. So there's some sampling that devices have to do. I have my data, and I have to sample a message from the conditional distribution over messages given my data. Right? This probability of m given xi. I need to be able to do that sampling quickly. Okay. I want to be able to do that sampling quickly, so the device time is fast as well. So ideally, you want all 5 of these to be low as possible. Okay, so before I start going into actual algorithms, any questions about anything so far? Yeah. So maybe I don't have a good answer. I mean, it probably matters, but from what I understand, in some of the deployments of these kinds of things, it's not the bottleneck anyway. Like for example, in this autocomplete and things like that, you do some stuff, and then it has to feed into training some ML models or whatever you're doing. And from what I get, I think server time might not be the bottleneck. And also, almost all the algorithms you're going to see today are heavily parallelizable. Like almost, if you have P machines, you can almost get linear speed up in P, right? So maybe that even makes it less of a big deal. But you'll see. But we're going to get some pretty big speed ups in terms of server time, from like quadratic time to linear. Okay, so a simple scheme. Let me first tell you some schemes that exist which are not ours. These are things that have been around for decades. So a simple scheme to describe is randomized response. So what is that scheme? Each device will send its true item x with probability e to the epsilon p. Otherwise, it will send a uniformly random other item in the universe, okay, such that each other item is sent with probability p. So what is p? There's only one value of p for which this sentence makes any sense, because the probability that you send something is 1. So the probability you send something is the probability that you send your true item plus the probability you send an item that's not your true item, which is that. That equals 1. You solve for p, and p is determined. So now this determines what the device does. How does the server estimate, let's say, the number of devices that are holding item x? It does some linear estimator. What do I mean? So imagine we have a counter, which is this f tilde x. And the counter starts at 0. For each message I get as the server, if the message is equal to x, I'll add alpha plus beta to my counter. If it's not equal to x, I'll only add beta. Okay. Well, if xi is equal to x, the expected contribution is alpha times e to the epsilon p plus beta. And if it's not equal to x, the expected contribution to the counter is alpha p plus beta. If I want this to be an unbiased estimator, it's not, maybe unbiased estimator is not the best thing to do, but it's the natural thing to do. Well, if I want this to be an unbiased estimator, I want the expected contribution in the first case to be 1, and I want the expected contribution in the second case to be 0, which gives me two linear equations and 2 unknowns, alpha and beta. So I solve for alpha and beta, and that determines what alpha and beta are. So that's it. The scheme is completely determined, because I told you what the device does, and I told you what the server does. And in fact, this can be implemented in linear time on the server side, because initially I'll just set all the f tilde x's to 0, and then I'll loop over the messages, and for each message, it'll cause me to add alpha to exactly 1 counter, and then at the end I'll add beta n to every counter. Okay, so the pro is that it's very fast for the server and devices. It's also low communication, meaning there's no communication overhead. Normally, sending my data would take log k bits, because it's an element in a universe of size k. The communication of this protocol is also exactly log k bits, because I'm sending some other possible element of the same universe. So I'm happy with that. The con is that if you go ahead and calculate the mean squared error of this, the expected mean squared error, it turns out to be very bad. I'm not going to do that calculation here, but just trust me. You'll see some plots. We did some experiments. It's bad in theory. It's bad in practice. There's another simple scheme to describe, which is due to Yi and Bard, which is the following scheme. Each device sends a random subset of the universe of size d. Okay. What's the probability distribution over these s's? If S contains x, x is your data. If S contains x, put probability mass e to the epsilon p on S. If it doesn't contain x, just put probability mass p on it. What is p? Well, for now, okay, d right now is just a parameter. We'll fix d later. D can be anything. By the way, if d is 1, this is randomized response. So this is like a generalization to larger d. So what is p? Again, there's only one value of p where this paragraph makes any sense, because the probability you send something is 1. How many sets are there that contain your element of size d? K minus 1, choose d minus 1. How many are there that don't contain your element? K minus 1, choose d. So that sum has to be 1, which means p is something. How does the server estimate f tilde x for any x? Very similar to before. For each message you get, if x is contained in that message is a set. If x is contained in that message, you add alpha plus beta, else you only add beta. Again, you can write down what the expected contribution to your counters are in the case that xi is equal to x versus not equal to x. You have two equations, you have two unknowns. The first one should equal 1, the second one should equal 0. You solve for alpha and beta. When you solve for alpha and beta, and then you go through the exercise of calculating the expected mean squared error, you'll get an expression that depends on epsilon, n, k, and d. D was a parameter. So you do some calculus, you choose the d that minimizes the expression, and it turns out that the best d to choose to minimize the expression is like the closest integer to that value, k over e to the epsilon plus 1. Now remember, for us, epsilon is a constant. It's like 5 or something. So think of the denominator as some like larger constant. So it's roughly k. It's proportional to k. So now, this new scheme, the device has to send a random subset of size k over 100. That's a very big message. The last protocol had communication log k bits. This has communication like k bits. It's exponentially worse. So the con is that the communication is terrible. Runtimes are also terrible because you have to deal with these very large messages. The pro is that it actually gets the optimal trade-off between privacy loss and utility loss. Meaning, for any epsilon, this gives you the best scheme in terms of utility loss for that epsilon. And when I say the best, I don't mean our usual TCS best of big O. I mean, it's 4 times whatever. Even the constant is optimal. It's really the best scheme. And that's something I want to emphasize right now because I know we all come from the TCS world where we usually throw constants under the rug, maybe even log factors under the rug. But remember, there were many things that we wanted to optimize. We wanted to optimize like run some device time, server time, etc. So the thing is, if your device time is 4 times something instead of 8 times something or whatever, or the other way around, if it's 8 times something instead of 4 times something, you're like, well, next year's iPhone will be a better CPU anyway, so like it's not that big of a deal. Or on the server side, you're like, well, if it's a parallelizable algorithm, I can just have more CPUs, throw more compute at it, and that will speed things up for me. But utility loss is like a law of nature or a law of your algorithm. You can't, if your utility is off by a constant factor, you can't improve your utility by spending more money on compute. It's just a property of your algorithm. Okay. So as you probably know, as you know, companies care a lot about getting the best kind of performance, right? Like what's my recall? What's my and the ML performance, like stat performance, right? Like what's the percent of queries where I get the wrong answer? I want that to be as low as possible, right? And utility loss at the end downstream has implications for the quality of the product and the service you're providing. So if I have bad utility for understanding my user data, that means I'm going to have worse autocomplete or worse spell correct or whatever thing that I'm trying to do. And that's like a no-go. I'm willing to spend a lot of money on, even if I have a slower algorithm, I might be willing to spend a lot more money running the slower algorithm if it gets me better downstream performance in my translate or in my autocomplete or spell check. So we really care about like utility loss, even the constant factor utility loss. Okay. So now let me tell you a meta approach. So that both of the previous algorithms fall under, which is the following thing. Suppose that, again, we have this universe of size k, and then we have a message space, capital Y. We'll associate with each x some subset of message space, S sub x, which I'll call the preferred messages for x. And let's say that every element of the universe has little less preferred messages. And suppose that these preferred message lists form some kind of combinatorial design. Meaning if you take 2 different data elements, like a picture of a cat versus me drinking from a bottle, x versus x prime, that are different, and you look at the intersection of their preferred message lists, all these pairwise intersections have exactly the same size, little l, script L. And what's the protocol? It's exactly what you saw last time. So for any message in message space, I need to attach a probability to that message of it being sent. If it's not a preferred message, if it's not an SX, it's probability P. If it is a preferred message, it's probably in the epsilon P. Again, what is P? There's only one value of P where this makes any sense because the probability that I send a message is 1. What's the probability that I send a message? It's the probability that I send a preferred message plus the probability that I send a non-preferred message. Okay, so solve for P. And again, the server is going to use a linear estimator, which is unbiased. So for every message I get, I'm trying to estimate now how many devices are holding data element X. For every message I get, if it's a preferred message for X, I'll add alpha plus beta, else I only add beta. Again, if xi equals x, I want the ith summand to have expectation 1, else I have expectation 0. I get two linear equations with two unknowns, alpha and beta. I solve for alpha and beta, and that determines the protocol. Okay, so for any such combinatorial design in any message space, I get some protocol. How good is the protocol in terms of utility laws? Right, of course, people agree. This is randomized response. All the preferred message lists are singleton sets that contain X itself. Subset selection. All the preferred message lists are the set of all size D subsets of the universe that contain my element. So the next slide here, there's some math. We don't really need to go through it line by line. Just the point of the slide is that a calculation can be done if you want to do it, and it's not that hard to do it. So if I want to compute the expected mean squared error, it's basically the sum of the variances of the f tilde x's. So you can compute the variances and get a closed form expression. And here I did this exercise. This is it. This is the closed form expression. I separated it as a sum of two fractions. And what I'd like to, just trust me on this, don't inspect it too hard. It turns out that the second summand is like a low order term. The first fraction is really the one that's dominant. You can think like that one that you're adding in white is just like multiplying this by a 1 plus a little over 1 term at the end of the day when we set our parameters. So ignore it. Okay. So the mean squared error depends on n and epsilon, of course. And then it also depends on the parameters of our combinatorial design. Script L, S, and the size of message space. Okay? And what this expression reveals is that the mean squared error increases as two things increase. The ratio L over S and the ratio Y over S. So you want the intersection, I mean, this is intuitive. You want the intersection sizes to be as small as possible. Okay, well, maybe it's not intuitive that it's the ratio, but you want the ratio between the size, the intersection size divided by the size of the set to be small, and you also want the size of message space to be small when you divide by the size of these sets, these preferred message lists. That's what comes out when you do the calculation. But the point of this is now it's a combinatorial design question, right? So this is something that I guess we in our community do, and we feel like we're good at. So how do you design some set system that optimizes these parameters? And you think and you try different things. You're not sure what works. Maybe at some point you turn to religion and you pray or something. Okay. And then at some point you ask someone who knows combinatorics very well. Okay, and he says, "Oh, just look very closely at this picture of yours, this religious picture, and notice the projective geometry." Okay, so the answer for us is going to be to use projective geometry. And let me just lead into why that's related. So here's a basic idea that's not going to quite work, and then we're going to fix it. So pick a prime Q and define message space as just FQ to the T. So all length T vectors over FQ, the finite field FQ. We'll pick T large enough so that the size of message space Q to the T is at least K. So T is basically the ceiling of log base Q of K. Now that message space is at least as big as the size of the universe, we can have some kind of injection from the universe into message space. Which means we can view every element of the universe itself as a vector in FQ to the T. And we can define the preferred message list of x as the t minus 1 dimensional subspace orthogonal to it. Okay, so all the u such that x dot u is 0 mod q. And then, of course, what are the intersection sizes? Sx intersect sy. It's a t minus 1 dimensional subspace intersecting another t minus 1 dimensional subspace. Basically, you have two linear constraints, right? U dot x is 0 and u dot y is 0 mod q. So this is a t minus 2 dimensional subspace. So that means that the size of S is q to the t minus 1. The size of L, the intersection sizes are q to the t minus 2. So you get that L over S and S over Y are both 1 over q. You try to figure out then what q would minimize this expression. Basically you basically want q to like 1 over q to cancel this e to the epsilon minus 1. So q is roughly e to the epsilon plus 1. Okay? So pick the prime as close to e to the epsilon plus 1 as possible. And that should have said plus 1, not minus 1. But this is wrong. Okay, why is it wrong? It's wrong for a very silly reason. There's already a hint. I already said projective geometry. So, anyone see what I slipped past you? Yeah. What if x and y are scalar multiples of each other? Then Sx intersect Sy is not t minus 2 dimensional subspace. It's the same subspace. It's t minus 1 dimensional. So yeah, exactly. That's the problem. So you fix it by using projective geometry. Okay. Actually, this slide doesn't really need to be here, but I just like it because I started learning some more about the Renaissance when I was working on this paper. Okay. So this is connected to the Renaissance. This algorithm. Okay. So not really, but kind of. Right, so what is projective geometry? I mean, I guess the motivating... Oh, okay. The motivation actually, I believe, comes from art. I mean, in reality. Why? So what is projective geometry? The idea is like, I'm a Renaissance painter, like Da Vinci painting The Last Supper. I mean, he actually did this, okay? Well, he used these techniques to paint The Last Supper, and as did a lot of other Renaissance painters. So what's the idea? The idea is, I'm the painter, I'm looking at a 3D world, and I want to paint it on a 2D canvas, okay? How do I properly, like realistically paint a 3D world on a 2D canvas? The idea is that, that's my eye, those lines coming out of that circle are, like that circle is the painter's face, and there's some lines coming out of their eye. And that line intersects the canvas at exactly one point. And the point is that every point on that line projects to the same point on the canvas. So lines become, the whole line is equivalent, and the line becomes a point. Okay? And I guess in this particular photo, you can see that this person is standing on some railroad tracks, I guess. And the edges of the railroad tracks are parallel, of course. And you can see on the canvas, what does that translate into when you try to draw it on the 2D canvas? The parallel lines actually are slanted, and they meet at infinity at this point that artists usually call the vanishing point. Okay. But anyway, this is just some historical background. We don't really care about the art for the sake of our algorithm. All we care about is that everyone on the same point through the origin, on the same line through the origin, is equivalent. They're the same point. Okay. So we'll define projective points in f2 to the t as non-zero vectors in f2 to the t, whose first non-zero is a 1. I don't mean whose first entry is a 1. I mean, as you scan from left to right, the first time you hit a non-zero, that non-zero has to be a 1. So you basically, there's a canonical vector that represents the line, which is, any point on the line, normalize it by the first non-zero entry so that it becomes a 1. Right? And all these points become equivalent. So basically, for any point in projective geometry, there are like q minus 1 other points that it could have come from. So the number of projective points is q to the t minus 1 over q minus 1, just because, well, you subtract 1 from the numerator because you remove 0, and then there are q minus 1 points that correspond to any canonical point. And then now you pick t so that that expression is at least the universe size. And then now there's an injection from your point set into projective points. And now your preferred message set, is the projective subspace orthogonal to x. all projective points u such that x dot u is 0 mod q. And you can easily do some calculations for what SL and L are. And the bottom line is if you set q appropriately, you set q to be something like roughly e to the epsilon, you get the nice SL and size of y that you wanted, and you're happy. And then here's the actual comparison to some prior works. So maybe the things I'll point out. Our two new mechanisms are these. This is the one I just talked to you about. This is one where you can basically, well, if you look over at the server time, we have an e to the epsilon in our server time, and maybe you don't like that. You can make that e to the epsilon be any prime q that you want at the penalty that you will worsen your utility loss by a 1 plus 1 over q minus 1 factor. So let's ignore the last row for a second. So the point is, compared to all the prior works, we match the best known communication, which is just proportional to sending an element of the universe. Compared to the utility loss, we also match the best known. This is actually the optimal utility loss, including the constant factor. And randomized response, of course, was super fast, great communication, but utility loss roughly n times k, right? Whereas we don't have the n times k anymore. And then subset selection got the optimal thing, but server time was n times k. Our server time is not n times k, it's like n plus roughly k log k. We do have an e to the epsilon there, and some prior works did not have e to the epsilon in their server times. They were faster, but their constant factors on the utility loss were worse. And if you remember, if at the end of the day I care about getting the best quality translation I can or the best quality autocomplete, I'm not willing to sacrifice utility possibly. Okay. So we also implemented every single algorithm on this slide, including ours. And I guess let me just maybe show this. This teal color is, okay, so maybe I'll take a second to explain this plot. Let me explain what the bottom right one means. These are randomized mechanisms, so their performance is a random variable. Utility is a random variable. Utility loss is a random variable. So what we did was we ran the mechanism like, I don't know, 500 times, 1,000 times. Each time we ran it, we observed what was the mean squared error this time. And this is the empirical CDF of the mean squared error. So for example, when x is 50 on the x-axis, that was like, what was the median mean squared error? And whereas at the 100th percentile, it's like, okay, every time we ran it, our mean squared error was below that. It's like, what was the worst mean squared error we ever encountered? And the y-axis is the actual mean squared error. So the teal colored curve at the bottom is our algorithm. And the blue curve is subset selection, which was the previous known optimal algorithm. And the point is we're basically on top of each other. Especially here, we really are on top of each other. But we're faster. We're like almost linear time as opposed to quadratic time. And the ones that had worse constant factors but were fast, indeed, even in the experiments, they really do have worse constant factors. Actually, the yellow is our hybrid algorithm that trades off time for utility loss. And then the red and the green were the ones that had worse constant factors. They really do have worse constant factors when you implement them. We also did a timing experiment. So kind of the previous state of the art, which had optimal utility loss, on my computer with reasonable size data, took about half an hour. Our new algorithm took 37 seconds. Our hybrid variant of our algorithm took about 6 seconds. And then there are faster algorithms that took a second or half a second, but they have worse utility loss, even empirically and in theory. One thing I didn't get a chance to say, I think I have like 4 minutes left. Is that right? Okay. Is why is our algorithm actually fast? What's the fast algorithm? And the idea is to use dynamic programming plus one more optimization. And let me say a little bit about that. So remember now, everything that's in every meta algorithm, meta mechanism that I described, you have these preferred message lists. You need to add alpha whenever for each x, you need to add alpha f tilde of x whenever you get a message that's in the preferred message list for x. I can rewrite this sum as this. Since you always add beta, you add beta n. So really the thing you have to do is count for every x, how many messages did I get that are preferred for x? That's really the thing you need to do for all x simultaneously. For projective geometry response, our new mechanism, what is the definition of Sx? It's vectors, canonical vectors u that are orthogonal to x mod q. So let's create another histogram y, where y sub u is the number of messages I got equal to u. And then this sum right here is the same as the sum over all u orthogonal to x of yu. So I need to calculate this sum simultaneously for every x. Naively, there are kx's, and the number of orthogonal u's is k over q. So naively, computing this sum for every x would be like a nested for loop, two nested for loops, would take k squared over q time. It'd be a quadratic time algorithm, which I'm not happy with. So you can do better with dynamic programming. And maybe I'll just say, try to get through this briefly. So let's just look here. I always like to think of dynamic programming as like recursion with memorization. And then later, if you want to implement it bottom up, which is what we did, you can do that. But let's just think about the recursion. F of a, b, z, I'm going to define it to be the sum of all yu such that the length j prefix of u is a, and the length t minus j suffix of u dotted with b mod q is z. This is my definition of f a, b, z. And the thing that I really want for f tilde of x is alpha times capital F of null x0. Right? This sum is this thing that I care about. This sum under this notation is the same as capital F of null x0. Because what does it mean? It means that the length 0 prefix is null. Okay, the length 0 prefix is always null. That's trivially always satisfied for any u. And then the length t suffix of u, well, the length t suffix of u is u. U is a t-dimensional vector. Dotted with b, b is x. So this just says that u dot x is 0. So this is exactly what I wanted. Okay, and then now I need to find some recurrence relation that lets me compute this thing. And there is a recurrence relation. I'm not going to go through it line by line, but just trust me, there is a recurrence relation. And if you do the kind of straightforward memorization, you would get a DP algorithm that takes k q squared t time and k q memory. Then you realize an optimization that, by definition, f of a, b, z is equal to f of a, b zeta inverse z zeta inverse for any zeta. Which means that you only need to calculate entries in the DP table such that beta b zeta inverse is either a canonical vector or the 0 vector. Which means you only need to really fill out a 1 over q fraction of the DP table anyway, which saves you a factor of q. So now your time is kqt with linear memory. Okay, and that's the algorithm. And in fact, this is the implementation of it. It's on GitHub. You can find it if you want. It's also possible, as I mentioned, to trade off utility for server time. So basically what you do is for any prime q, you can worsen utility by a 1 plus 1 over q minus 1 factor, but speed up the runtime by an e to the epsilon over q factor. And the way that you do it is you break up the universe of size k into h blocks, each of equal size k over h. On the device side, you reveal your true block with some probability. Otherwise, you reveal a random block, which is basically randomized response on the blocks. And then you do projective geometry inside your block. And then you can analyze that. And that's it. What next? There's some open problems. This is the last slide. There's one thing I kind of swept under the rug, which is, remember, you need roughly q to the t to be k. Which means t is the ceiling of log base q of k. Which means you might end up working over a universe that's a factor of q larger than you really needed just because of a rounding issue. Which means your runtime and your memory end up being a factor of q larger than you really needed. And q is like e to the epsilon. If epsilon is 5, e to the epsilon is like 150. So your code becomes like 2 orders of magnitude slower because of this silly rounding issue. So is there a way around that? You basically want a better combinatorial design that works for more values of the parameters. And also sublinear algorithms on the server side. You can in principle hope to have sublinear time recovery algorithms. Ours is linear, almost linear time, not sublinear time. So that's all I have for you. Thanks. Any questions? Yeah. Yeah. So the unfortunate thing is, in this design thing, I said that the intersection sizes all have to be L. At most L doesn't work. So like if you do something random, you'll probably get some intersection size at most something. At least the way that we are doing things. Yeah. Maybe. Yeah, but okay. Also, you want a fast algorithm. I mean, there's already. I talked about subset selection. There's already another algorithm from like I think ICML 2021 called PyRapport, which already has a quadratic time recovery algorithm. So really, one of our main things is it's almost linear time. Yeah, so that's another reason why a random construction wouldn't work, because it wouldn't come with a fast decoding algorithm. Okay, yeah. Yeah. Yeah, I'm happy to, but I don't know what. So the question was, we use the linear estimator for tilde, why not do some other kind of estimator? If something works, I'm happy to do it. I just don't know anything else. Yeah. Yeah. Oh, so you said in the runtimes were there big O's? There are big O's in the runtimes, but I mean we did run timing experiments, and I guess you mean like for example the hybrid projective geometry response. Yeah, I mean it's so the thing is if you saw from the dynamic programming, there's a factor Q in the runtime, and the point is Q is supposed to be like e to the epsilon, but the hybrid thing when you combine it with randomized response, you can basically run some version of the algorithm with Q being like 5, for example. Right? So the factor of Q becomes less of a penalty in your runtime. And that's real. I mean, we're not trading off a better asymptotic runtime for a worse constant factor. We're not hiding anything there. It really is faster. Because it's the same algorithm. It's the same algorithm over a smaller Q. Yeah. Are there trade-off theorems? No, I mean, for all we know, you can get everything optimal like at the same time. Linear runtimes on the server, as fast device time as you want, optimal for in your utility loss. Yeah, there's nothing stopping us from hoping for this. Sublinear time, server time even. This is the last one. Yeah.
So it seems like the best area to get is like some constant times 10.
Yeah.
That means like most elements are being approximated with like added errors for rhythm. Kind of an average.
Most elements have an error root end. Right?
Nice, yeah.
Yeah.
Do you think that's like a meaningful guarantee? Because n is kind of like really as a letter, or do you think we should make better or like different assumptions to get like a more meaningful guarantee? Like for example, assuming certain recipient and maybe.
Yeah. So the question was, if you look at the forms of the error, the mean squared error. The expected mean squared error was roughly like n, 4n over e to the epsilon or something, which means the typical element is off by root n. Your estimate of its frequency is off by root n. The question was is that meaningful? And perhaps we can hope to get better bounds for like special kinds of frequency vectors like Zipfian decay and things like that. To the first question, okay, so I'm not close to the people who are actually running these things in real life, but from what I hear, people are running, I don't know about our algorithm, but they are running algorithms that solve this problem in real life. So I guess it does produce something meaningful for them. I don't know of any work that gets better error for these problems if you assume something about the frequency. Any last questions? Yes?
So this preserves the privacy of the messages, right?
Yeah.
But what if a device sends...
Well, the privacy of the data.
Correct. So what if a device sends lots of messages? Then
what if the device sends a lot of messages? So it's... so you're saying like what if each device doesn't hold a single XI, but it holds like a database? You're right. That what I talked about today would not support that. I don't know in real life. I don't know what they actually do. I think they might just in reality sample a random element from their database. So look at all the recent messages that they sent and sample a random word or sample a random program or something like that. Okay,